Welcome to aminacademy.com. In physics, let us discuss about speed of transverse and longitudinal waves. First, we'll discuss about speed of a transverse wave. Have a look at the water of a stream. The speed of a mechanical wave is determined by the restoring force set up in the medium when it is disturbed and the inertial properties, that is mass density of the medium. The speed is expected to be directly related to the former and inversely proportional to the latter. For waves on a string, the restoring force is provided by the tension T in the string. The inertial property will, in this case, be linear mass density mu, which is mass m of the string divided by its length. Using Newton's law of motion, the exact formula for the wave speed on a string can be derived, but this derivation is outside of our video, so we'll discuss about only the formula. Here, before looking about the speed of transverse waves, first we have to understand the terms. Amplitude. Amplitude can be defined as the maximum displacement of a particle from its equilibrium position. Wavelength, the distance between one peak and the next peak or one trough to next trough is known as the wavelength. Period, the time it takes for two successive peaks to pass through a fixed point is known as the period. Frequency, the number of wavelengths that travels through a certain point in a second is known as frequency. Number of waves per second pass through the particular point. The speed depends on two factors, the wave and where it traveled through. That means the medium. The speed of the wave depends upon the wave itself as well where through the medium it travels. To understand this, let's take transverse waves example in real life. Waves travel faster in deep water than a shallow water. Let's take two ropes of different widths as a thin and thick rope. Let us generate a pulse or a wave in these two ropes. Wave in the thin rope, wave in the thick rope, we will differentiate. Now, looking at these two images, that means you might wonder which wave in which rope would have a greater speed. The wave would pass with a greater force in a thin rope, but how it is? Let's assume a thin rope as a pipe with a large diameter like this. The water flow would be fast between the large diameter water pipe would allow high flow easily. Now let's assume the thick rope as a water pipe with a smaller diameter. Now if the same energy level water passes through this thin rope, there will be a greater vibration between the water molecules as they possess higher energy and higher momentum. From these two examples, we conclude that waves would pass easily through a thick rope. Thick pipe means thick rope. We know that the velocity of the transverse wave is V equal square root of T over mu, where V equal to wave speed or velocity, T equal to tension in the string, Newton per meter, and mu, the linear mass density, that is mass per unit length measured in kg per meter. Now, this is the formula for wave speed is square root of T over mu, you have to remember. This velocity is directly proportional to the square root of the tension in the string and inversely proportional to the linear mass density. The speed of the transverse wave decreases with an increase of the mass. But how it's happened? Let's say Now, next one, longitudinal waves. What is longitudinal waves? Longitudinal waves, such as sound, are transmitted through media with velocities depending on the densities and elasticity of the substance. Sound has a velocity of about 0.33 kilometer per second, that is 0.2 miles per second in air, and 1.5 kilometer per second in water, and 5 kilometer per second in steel. These are some differences that the speed of the sound pass faster in solids than liquid and gas. A sound wave is an example of a longitudinal wave and is produced by the vibrating motion of the particles that travels through a conductive medium. An example of sound waves in a longitudinal direction is the tuning fork. In sound waves, the amplitude of the wave is the difference between the maximum pressure caused by the wave and the pressure of the undisturbed air. The propagation speed of a sound depends upon the type, composition of the medium, and temperature through which it propagates. A longitudinal wave is one where all the particles of the medium, such as gas, liquid, or solid, vibrate in the same direction as the wave. Sound waves are longitudinal waves. When longitudinal waves travel through any given medium, they also include compression and rarefactions. Longitudinal wave formula is y of x comma t equals y of 0 cos omega t minus x over c. This is the expression for the longitudinal wave formula, where y is the displacement of the point on the traveling sound wave, x is the distance the point traveling from the wave source, t is the time elapsed, y0 is the amplitude of the oscillations, c is the speed of the wave, omega is the angular frequency of the wave, the quantity x by c is the time that is wave takes to travel the distance x. The frequency f of the wave is given by the formula f equal to 2 pi omega. Hope you understand what is the longitudinal wave along with this formula. Now let us discuss about the principle of superposition of waves. Look at this figure. Here three waves, sinusoidal waves passing here, and look at here some two waves meet some points, that is here green and red meet here and another meeting point, like, and look at here this point is red and blue meeting point here, the same here red and blue meet here. These are the points of superposition. The principle of superposition of waves, it tells us that when two or more waves overlap in space, then the net resulting disturbance is equal to the algebraic addition of the individual disturbances of the respective waves. When two or more waves move through a similar medium, they are likely to interact. That means that the net amplitude caused by two or more waves traversing the same space in the sum of the amplitudes that would have been produced by the individual waves separately. For example, two waves traveling towards each other will pass right through each other without any distortion of the other side. Now, further we will discuss about what is superposition. What happens when two waves pulses traveling in opposite direction cross each other? It turns out that wave pulses continue to retain their identities after they have crossed. However, during the same time overlap, the wave pattern is different from either of the pulses. Shows the situation when the two pulses are equal and opposite shapes more towards each other. So far, we discussed about principle of superposition and longitudinal wave formula, as well what is wave speed of transverse wave, and what is rope wave, and what are the factors affecting the speed of waves, and some definition of amplitude, wavelength, period, frequency of the waves. We have done. Please subscribe our YouTube channel.